looking for questions if anybody's got them from chapter 10. I know you guys did some review stuff and probably started working on the problem set pretty deeply and studying and all that. So if anything's come up, we'll do any last minute chapter 10 stuff here today. Okay, well, if that changes, you can always hit me up. You know where to find me, and I'd be happy to do that again. So today, since we don't have any old questions, and that's maybe not so surprising, you guys are pretty assertive about your question asking, so that makes sense to me. We're going to start chapter 11. Now, probably realistically, I could do chapter 11 in one day, but we're not going to do that. But just to let you know, this is short chapter, not too difficult, so we won't be here for very long, just giving you a heads up. But it feels like a bad idea to do this in one day and basically take 2 tests next week. You know what I mean? All right. So we're going to start off here in chapter 11 talking about the complex plane. So a little bit of review back from Algebra 1. So the imaginary number. We call, what do we call it? I. And what's I equal? Square root of negative 1, which is the same thing as saying I squared would equal negative 1. Sheepers creepers, guys. So once we've defined this imaginary number I, we can form the set of complex numbers. Which are the things of the form a plus bi, where a and b are real numbers, and I is this complex number. You guys all kind of remember this from last year. Note that one of the key features of the complex numbers is they're not orderable. So, for example, the real numbers are orderable. Say if I wanted you to list from least to greatest, and I give you like 5, 6, and like 0.87, and like 7/9, and then like 18, 30, or 20 seconds or something. Like these are all things that we could write in order, right? And maybe let's throw in there like the square root of I don't know, something 1/3 or something, I don't know. Right, how would I figure out what order to write these in? Oh, come on, guys. How could I do this? Turn them all into decimals. Yeah, and then we just sort them by the size of the decimal. That's exactly right. So like 5/6 is this guy, and 7/9 is this, 18, 20 seconds is this, and then square root 1/3 is this. So like that's the smallest. And then it was this guy, I think. And I don't remember there. So this one is bigger. Yep, okay. So we have this one, and this one, and this one, right? Everybody's okay with that idea? Now, these are all just real numbers. What if we asked you to do the same thing with complex numbers? You know, what if I give you like a bunch of complex numbers and I ask you to order them from least to greatest? Doesn't really make sense now, right? So this is actually not possible. Because if you think about it, well, should you sort by the A or the B? You know, like, but why would it be greater if the A is bigger, but then the B is smaller? Like if you compare just these first two? Sure, the A is bigger for the first one, but the B is smaller in the first one. So like, why would that mean that the first one's great? You know, it's just like, what do I do with that? So because these aren't sortable from least to greatest, what that means is if they're sortable by least to greatest, we can put this on like a number line. Because these are not, you cannot put this on a number line. So what are we going to do with these then? We need to use a two-dimensional system to plot it, i.e., what we'll call the complex plane. So on the complex plane, the horizontal axis, we refer to the real axis. And that's where we plot the real part of our complex number. And the vertical axis is the imaginary axis. And that's where we plot the imaginary part of our complex number. So to just kind of get an idea what's going on here, let's say we want to plot the real or the complex number 4 plus 3i. So we're going to go 4 on the horizontal, on the real axis, and then 3 on the imaginary axis. Oops, those all should have eyes at the end of them. And I'm going to plot this one in blue as I've indicated there. Or if I want to do 2 minus 4i, I'm going to do 2 on the real axis and negative 4i on the imaginary axis. So I have something like that, right? Is everybody okay with that idea? Very simple, right? Just like plotting a point. Okay, so if this is how we're plotting these numbers, just like how when you learned how to add real numbers, you learned how on the number line you just kind of, okay, if I'm doing 3 plus 2, I count 3 over, and then I count 2 more over. You guys remember doing that? We could do the same thing here. So we're basically counting 4 over and 3 up. And then from this spot, we're going to count, boy, I did not write the right thing there at all, did I? We'll count 2 over and then like 4 down. And this spot here would be like 6 minus 2i. Now, just like in elementary school, when you learned how to add numbers, you gave up doing it on the number line pretty quick, right? We're going to give up doing this on the complex plane pretty quickly, because the big takeaway here is that if I take 2 complex numbers and add them together, what I'm really doing is just adding the real parts together and then adding the imaginary parts together. That ostensibly all we're doing is combining like terms there, right? And I guess we could do this as plus or minus. Is that okay? And then similarly speaking, if I take the same complex number and add it to itself, what am I going to get there? Two of them, right? Now, typically we think about it kind of this way, as more of a distributive thing, right? And this is the piece usually we are interested in. So if I wanted to say compute and say we have Z1 is like, I don't know, 6 minus 2i, and Z2 is negative 3 plus 5i, and then maybe Z3 is negative 3i. And we want to do like 2zi, or Z1 minus 3Z2 plus 5Z3. Well, all I'm really going to do is just kind of plug everything in. and then distribute things through. And then we'll just combine like terms. Right, pretty straightforward. Nothing tricky here, nothing surprising even, or really that unusual. As an aside, your calculator can handle doing problems like this as well. You don't have to do these by hand if you didn't want to. To do that, though, your mode needs to make sure you're in the complex number mode. But you can just kind of type in what we had here, and your calculator can handle that for you. The I button is second, and then the decimal point. Oops. And we can just type this in exactly like it looks on our sheet of paper. Paper. Our sheet of paper. Uh-oh, what did I do wrong here? Oh, ha. That's what I missed, my negative sign. There we go. And it supports exactly what we did there, right? Cool. Nothing complicated, right? All right. So on to the next topic. So for some real number a, what does the absolute value of a mean? Not what is it equal to, but like what does it mean? Anybody remember? Yeah, great. I'll just say is the distance from A to 0 on the number line. And let's just, maybe I'll change that to a letter that looks less like an article in my sentence. Maybe I'll make that a K. So it doesn't look like A is a letter, you know, A isn't my number. Yeah, it's just kind of a confusing letter to pick there. You guys get what I'm saying? Because you read that sentence and it feels like A is a word rather than a symbol. If I put a K there, that's pretty clear that it was what we're talking about. Okay, great. So what does that mean? Well, so if I have some complex number z, where z equals a plus bi, then what does the absolute value of z mean? The absolute value of a real number is the distance from that number to 0 on the number line. What's the absolute value of a complex number have to be? Nope. Nope, we can do this. Nope. It's a distance from that number to the origin on the, nope, can't put imaginary number or complex numbers on the number line, on the complex plane. Right? Because that, where do we put complex numbers? On the complex plane. So if I think about this here, let's say this is our point A plus BI. Here's the origin. And Mackenzie, if you said 0 there, that was not inappropriate, because that is that's the number. Oh, Mia, you said it? Oh, Emma, yeah. Saying 0 there was not inappropriate. It came from that back corner. I couldn't tell who it was. Since 0, that origin is the number 0, like 0 plus 0i, which is 0. So what does this distance got to be? Well, that's just the distance formula, right? So what can I say then? That looks pretty familiar, guys, doesn't it? What does that look like to you guys? Oh. Looks like the Pythagorean theorem. Yup. The what?
The square root formula. It just seems a bit away.
Distance, well, we use the distance formula right here to get it. So sure, it does look like the distance formula. Absolutely. How about something we've just been doing? Remember in the polar coordinate system, that r squared is equal to x squared plus y squared, right? What's a basically the same as? An x coordinate. What's b basically the same as? A y coordinate. And r would be the radius of the circle that passes through that point that's centered at the origin. Still basically the same thing. Okay. So this symbol here, the absolute value of z, we can call it the absolute value of z. That's fine. Or sometimes we also call it the modulus of z. The modulus is just a fancy math term for basically the distance formula for something. So like in 1 dimensions, the modulus is just the absolute value. In 2 dimensions, it's this distance formula. In 3 dimensions, it might be a different distance. It's a slightly different distance formula. We talked about that a couple chapters ago when we did 3-dimensional vectors. You know, but maybe our distance function is like, you know, define something differently. Like if you're on a road network or whatever, you know, like you have point A and point B here. Maybe you have to take roads. So like this is how your distance function needs to work, because you can't go from straight A to B because the roads don't go straight from A to B. You have to take like a grid, right? So like these are all things that are like, we just give it a generic term so you don't have to be like super specific, because like if you're doing something with a modulus, kind of all the rules are the same. So that's where this word modulus is coming from. And you might, if you do a lot of mathematics or engineering, you might bump into that term later on. But that's all we're basically talking about. It's just like the distance function for whatever system you're working in. And you get how, like, in a road situation, like the distance function is no longer the distance formula for like how a car would have to travel. You know what I mean? If you're in a city where like you're on a grid. Anyways. Okay. So that same distance we might call r. And this angle theta, what can we say about theta there? Oh, come on, guys. Oops. We can say that tan theta is equal to B over A. Is this starting to look familiar? What did we say last chapter, or in the last chapter theta was? Said tan theta was y over x. What's B basically? A y coordinate. What's a x coordinate? So still the same thing, right? We're going to give this angle theta a fancy name here also. We're going to call this the argument. So the argument of a complex number is basically that angle theta, that it standard position angle that it makes. Now, if you take these two ideas together, we can describe that complex number that way as well, right? Just like how we could convert polar or rectangular points to polar points. This is going to give us something called the trigonometric form. Trigonometric?
No, behind it.
Argument? So the trigonometric form is, let's write it this way. Is r times cosine theta plus I sine theta. So that means that if we have a complex number in the standard form, that's what we'll call this. That's the same thing as r cosine theta, r sine theta. So that's basically, what's the relationship between our standard form and trigonometric form? It's analogous to the relationship between a rectangular coordinate and a polar coordinate, right? Everything that you convert back and forth between them basically the exact same way. They're two different mathematical objects, but like the structure between them is identical. So for example, let's say we want to convert negative 2 plus 5i to a trigonometric form. So let's give that a name. I'll call it z. Z is kind of the standard name you give complex numbers in mathematics. if you're picking a letter to represent a complex number, typically we use z's. It's not wrong to use different letters, but that's kind of the convention. That's why I'm using z all of a sudden, if you're curious. Most of you probably weren't. So we need two things. We need the r, which is the same thing as the absolute value of c. So that's negative 2 squared plus 5 squared, all square rooted. No problem there. To get theta, we'll plot our complex number. So this is the theta. So to find theta, I'm going to need my angle alpha. And the other arm of alpha is at 180. Actually, let's say pi, because let's make this be specific. Let's say where theta is between 0 and 2 pi. Let's use radians here. I don't know why, I just felt like it. Everybody's okay? Feels like it's been a minute since we've done something in radians, so let's just do this in radians, you know? Don't want to ever get too far away from those, since they're just less familiar feeling, you know what I mean? Anyways, so what can I say here then? Theta is going to equal pi minus alpha, where alpha is the tan inverse of b over, the absolute value of b over a. So when I type this all into my calculator, I get about 1.9513. So the trigonometric form for mine is square root 29 times cosine 1.9513 plus I times sine 1.9513. And that's my answer. Is that okay? Pretty easy, right? Is this really any different than what you just got done doing? The process is ostensibly the same. What if we want to go the reverse? Yeah, let's do something. Do that. Oops. So let's say we want to convert this trigonometric form complex number into a standard form complex number. Well, all I'm going to do is distribute through that square root of 11. Everybody's okay with that? That's supposed to be 3s. I mean, it could be, we could do it as 7 pi over 4. It wouldn't be, you know. Oh, I mean, they're supposed to be 3s. They're just, you know, you got Mr. Kulik handwriting to deal with. My apologies. Totally fine to ask clarification on my writing, though. I know that sometimes I get a little bit messy, especially at the end of the day, at the end of the week, you know? You get tired and your handwriting goes. You guys ever experience this? I bet your end of the day notes look way worse than your beginning of the day notes. Anyways, everybody so far so good? All I'm going to do now is I'm just going to compute sine of and cosine of 3 pi over 4. I recognize 3 pi over 4 is a unit circle angle. If I go and I look that up on the unit circle, what's the cosine of 3 pi over 4? It's negative root 2 over 2. And sine is positive root 2 over 2. So when I combine this together, I get negative root 22 over 2 plus square root positive root 22 over 2i. And that's it. Mr. Kulik, is it always going to be that easy? No, it could be easier, right? How would it be easier? I mean, if these angles were like 72 degrees or something where all you can do is type it in your calculator, I think that's maybe easier. And you just get like a cuckoo decimal and like whatever, that's what it is. Could it get harder? I don't really think so. So far, how do we think? Pretty easy? Okay, good. I'm going to stop here then. Yeah, what's up, bro?
What did you do to get 2 or square root 2 over 2? You just
Use the unit circle?
okay, just making sure. Just typically circles.
So that covers the first section. We're going to stop there because, like I said, I could do this whole chapter in a day if we really wanted to, but I don't want to do that. At this point, you guys could be able to do 1 through 40. We have, 40 minutes left of class. Boy, I think you could probably knock that whole thing out and not have to worry about it at all next week if you took some time and were so motivated. I'd suggest that you get motivated and do that because, boy, that makes next week a whole lot easier not to have to worry about these 40 problems that you banged out today in class because you were like, you know what, I could sit here and kind of space out for 40 minutes, or I could just get this done right now and then not have to worry about it next week. And boy, that sounds pretty freaking great. You know what I mean? Anyways, we'll stop here. If you have questions or whatever, feel free to bother me. It's no bother at all. It's my job.